All right, final exam review. All right, so here's the last one I was covering with you guys was number 47. Suppose a bug is jiggling up and down and swimming toward you at the same time. Compared to the frequency of the bug is emitting waves, the frequency of the waves is reaching you. All right, now I know it did this one, but okay, draw this game. All right, so the bug is jiggling up and down, sending out waves, right? Now the waves are traveling in circles, right? Because once he's released the wave, it's just into the environment. It's going at whatever speed it's going through that medium. In this case, maybe water. What if he's also swimming to the right at the same time? But he's like catching up with the very waves that he's sending out. Now, they'll still be circles, right? But they're not going to have the same center anymore because it's like swim to the right. Right. So, ask you guys a question that is not on the final exam, but could have been, just got bumped. What happens to the speed of the waves? Does the speed of the waves change? No, the speed of the waves, whatever it is, say through water in this case, right? But the frequency of blip, 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 is hey, that's more frequently those wave crests, or these could be wave crests, right? Like if you look down on the side, there's it bloop, 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 behind the bug like that. Right. So you guys kind of go, the frequency of the waves reaching you would be higher if the bug is swimming towards you. Okay. Is that called the Doppler effect? That's what that is. All right. Okay. And then the bell ring and all new stuff. As the sound of a car's horn passes and recedes away from you. Ooh, this sounds like the Doppler effect also. The pitch of the horn seems to, hey, is that decrease? Is that a decreasing pitch? Decreasing pitch. Child swings back and forth on a playground swing. If the child stands rather than sits, the time for a to and fro swing. Ooh, right? So one way to figure this out is to go through the time period for a pendulum. Okay? So let's look at a swing. Right, so swing seat right here. All right. So far these are looking identical. Maybe these are swinging back and forth. It takes some time to go back and forth, and the time it takes is equal to. Does anybody remember before I write down the formula? How much time does it take to go back and forth? It's 2 pi times square root of L over G. Right? I think you guys did that lab back in January and found that. Right? Right. So okay, so there's some length here. Right? No, let's put a kid on the swing. Let's have this kid standing. Make him exaggerate a little bit standing, right? Just so this effect is really more obvious, right? Versus this kid, I'm gonna have like sitting down. All right, so there you go. Okay. Now, if you look at the center of mass of each kid, here's the center mass out of this kid. Here's the center mass out of this kid. Right? You look at these lengths. Okay. Here's the effective length of the kid that's standing. So I'll call it maybe like L1. Right? Versus, look at this longer length right here. This could be L2. Right? So you guys see if you're sitting, the effective length of the pendulum was longer, right? Now, route this back to the time period formula. If you have a longer length, is that going to take more time to swing back and forth? Right? You see? Is that right? Suppose a simple pendulum is suspended in an elevator. When the elevator is accelerating upward, the time period for the pendulum. Let's go inside elevator here. Is that elevator? Right. There's you standing in the elevator, right, and you brought your pendulum, swing it back and forth. Right, take some time to swing back and forth. The time it takes to swing back and forth. Okay, we got 2 pi times the square root of L over G. So we got that. Right. So the length is whatever it is. Okay. Hey guys, if this elevator is accelerating upward, put some upward acceleration on here, then you inside the elevator, do you feel really heavy or really light? Really heavy. That's like somebody just turned up the gravity field. Right? Right, so let's go over to this time period of the pendulum formula. Right? Well, if you pump up this gravity field, make this denominator larger, 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 what happens to the time period? It gets smaller. Right? You guys see an inverse type relationship? Right? That probably makes sense too. Like if we're in a strong gravity field, I bet this would be swinging back and forth like, right? Versus if you took this to the moon, which would be like the opposite case, you think it'd be like on the moon, back and forth. I can actually modify this formula a little bit too. So I can do g plus or minus a down here, right? Now, if you're accelerating upward, you take the plus, right? Okay, so you're pumping up that artificial gravity. Right? So yeah, so elevator accelerating upward, the time to swing back and forth would decrease, is that inverse relationship. A sound wave that has a higher frequency, has a wavelength that is, so wave formula. Do you guys remember for waves, speed of a wave is equal to wavelength times frequency? That was the main formula for waves, right? So we got speed, we got wavelength, right, and frequency. Right? So if we're talking about sound, the speed of sound is whatever it is for some temperature and pressure in a room. Right? Let's say in this room, it's probably pretty close to 340 meters per second. Right? The frequency, that's like think like a musical pitch, right? Hit different musical notes at different frequencies, right? And okay, there's some wavelength, maybe distance between pressure points for this wave propagating across the room through the air, right? So this is a higher frequency. So if you increase this frequency, right, what happens to the wavelength? Right? Actually, has a different question first. What happens to the speed? Does the speed just stay the same? Like, if they're talking a high pitch, they're talking a low pitch. Are all those waves traveling across the room at the same speed? Yeah, they are. Right? So this number is locked in place. That's constant. So if you increase the frequency, something else has to give. Do you guys see an inverse relationship between these two? Frequency and wavelength? Right, so the wavelength would all right. Yeah. Right. So you guys see, like if you double the frequency, you get half the wavelength. Right? Double the frequency, by the way, is like going up an octave. All right. A leaf on a pond oscillates up and down 2 cycles each second that the wave passes. Right? So you can, right, okay, let's do a leaf on a pond. So here's a leaf. Maybe it's like blip, 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 blip. Right, here's like a wave passing by, right? What if it was 2 cycles per second? That's like blip, 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 blip. That's pretty close to 2 cycles per second, right? Guys, what's the frequency? Is it 2 hertz? Yep, 2 hertz. Right? Oh yeah. 51. Okay, a sound wave that has a higher frequency has a wavelength. Yeah, let's go back. So here's speed equals wavelength times frequency, right, for a sound wave, or well, for any kind of wave. All right, so it's any kind of, including sound waves. No, you're talking a high pitch or low pitch. That's different frequencies, but they're all the same speed. So the speed number is locked in place for some given pressure and temperature. Right? So we'll keep that controlled. Right? Here, let's do some numbers. Right? Let's try. What if you have 340 meters per second? That could be equal to. What if you have a wavelength of 34 meters and a frequency of 10 hertz? Right? You have something like that, right? Or what if you change this? Now I'm going to leave the speed locked in place, 340 meters per second. Right? What if I have half the wavelength? So it could be like 17 meters. Well, wouldn't I need double the frequency, 20 hertz? You can try that in your calculator. I bet that's going to multiply to also be 340 meters per second. Right? So let's see, how's this worded? Higher frequency. Right? You guys see, I just doubled the frequency, and I'm getting therefore half the wavelength. Right? There's an inverse relationship between these two right here. Inverse relationship. Okay. Right. So one increases, the other decreases. Right. You guys got that? Okay. All right. All right. Then this pond. See if it was 2 cycles per second. That's called 2 hertz. You could also say the time period between blips is 1/2, which is half of a second. Time period and frequency are reciprocals. Frequency and time period reciprocals of each other. So all right. All right. That's extra detail there. All right. Radio waves travel at the speed of light. True, because radio waves are electromagnetic waves, and all EM waves travel at that speed, right, through a vacuum is true. The wavelength of a radio wave received at 200 megahertz. Ooh, what was the wavelength associated with that? By the way, whenever you tune into an FM station, say you tune into like 99.9, right, that number has units attached to it, and those units are this right here, megahertz. Now, part of the trick of this one in particular is gotta do some conversion, right? We have to break out the same wave formula. We go speed equals wavelength times frequency, right? Of course, you guys have that written down because we were just using that. Except I made a modification. I'm using a special speed of light. Okay. So they gave us the number 300,000. Now the unit is kilometers per second. The wavelength we're trying to get, and the frequency, yeah, they said 200 megahertz. Okay. So I'm seeing some prefixes flying around. Guys, kilo, that's a factor of a what? 1,000, right? So I'm going to tag on 3 more zeros. So I'm going to say 300 million meters per second. That's called 3 times 10 to the 8 meters per second, isn't it? You guys seen that number plenty of times, right? So what's the wavelength? Lambda is wavelength. Okay. Ooh, mega. Guys, mega is a factor of a what? What is mega? Is a mega? Million? Yeah, right? That's like 10 to the 6. So I'm going to keep the 200, right? Then I'm going to tag on 6 more zeros, expand it by a factor of 1,000, or sorry, a million, right? And that's hertz, right? So now I got everything in base SI units. You guys know hertz is like 1 over seconds, right? So that's going to cancel with this some number of meters for wavelength. That 3 divided by that 2, then the seconds of hertz go away. Okay. Lambda is whatever 3 over 2 is, that 1.5, and then the unit would be meters. There you go, 1.5 meters. All right, that's good. Of course, when you guys get your exam, those numbers could change. What if they give you a different radio station? Right, you could. So same type math, right? Sound waves cannot travel in. Ooh, guys, where can sound waves not travel? A vacuum, right? Scream in space, no one can hear you. Right, so sound needs a medium to go through. All these other kind of medium. Noise canceling earphones. That's an example of what? Is that destructive interference, right? So noise canceling earphones, right? You turn them on, the battery operated. They'll take all the high and low pressure points. They'll swap them, interfere it, and that'll cancel all the sound. So it's destructive interference. Noise canceling earphones. The speed of sound in dry air at 20 degrees Celsius is 340 meters per second. Right? Yeah, we were just kind of using that number. How far away is a jet plane when you notice a 2-second delay between seeing the plane and hearing it? Right? Or you could change the story and you can make it between lightning and thunder. Suppose you see a flash of lightning, then you count 2 seconds and you hear the thunder. Right? How far away? Right? So let's see. There's a time delay. There's the speed it's traveling. We want to know what's the distance. Hey, does that sound like distance equals speed times time? Right? That's one of the first formulas you ever used in this class. Right? Distance equals speed times time. Right? You're going 70 miles an hour on 995. You do that for 2 hours. Got 140 miles. Okay. So in this case, I want to know how far. So silence for how far. Okay. It's going 340 meters per second. And there's a 2-second time delay. 2 seconds it's been going for. It's at 680 meters. Right? Guess that? Okay. So fill in a little bit more to the story. Guys, what if there was a 3-second delay? 340 times 3. Is that really, really close to 1,000? Right, really close to that, which is like a kilometer. Right? So a good rule of thumb is if you see a flash of lightning and then you count some number of seconds before you hear the thunder, every 3 seconds corresponds to approximately another kilometer away. So if there's a 9-second delay, that'd be like 3 kilometers. Right? Or if you like it in miles, it's about every 5 seconds corresponds to a mile. Right? It's about the same. Right? Which of the following are fundamentally different from the others? Fundamentally different. Let's check out this list. We got X-rays, radio waves, gamma rays, sound waves, light waves. Ooh, out of those 5 options, 4 of those are categorically the same, and 1 is completely different. Guys, which one's completely different from the other 4? Sound, exactly, sound waves, right? Why? Because guys, the other 4 are all what type of wave? Yeah, they're all, so X-rays, radio, gamma, and light are all electromagnetic waves that are transverse and travel at the speed of light through a vacuum, possibly, right? But not sound waves. Sound wave is longitudinal, which say it's a pressure wave. It travels about 1 million times slower, needs a medium to go through, all that stuff, right? The main difference between a radio wave and a light wave. Okay, guys, radio waves and light waves, are those both on the EM spectrum? Yep. Do they both travel at the speed of light? Yep. But they have different wavelengths and different frequencies. Is that true? Right. So I bet either of those could be good answers, wavelength or frequency, but not speed. So, so speed is out. I see wavelength, so maybe I'll just pick that one. You guys think? Right. Yeah, the other good option would have been frequency, but that's just not an option. Okay. The main difference between a radio wave and a sound wave is, do you guys think basic nature would be good? Right? Because wavelength, I mean, they could have similar wavelengths, you know, maybe some number of meters. Energy, amplitude, frequency, yeah, those could be comparable, right? But the basic nature is what we're talking about, right? One's a transverse wave going through possibly a vacuum of space. The other is a longitudinal wave traveling way slower through a medium. Compared to its speed in air, the speed of light in water. Ooh, you guys remember when a light ray hits water or glass, it refracts, right? And that refraction was kicked off by, well, this step here, that the fact that it slows down, right? You guys remember that? Light slows down, right? So light goes at the speed of light, really only through a vacuum. Through air, it's like almost that, so you can pretty much kind of round it to that anyway, right? But through, here, give you guys some indices of refraction. You guys remember N is index of refraction, okay? And that's like C over V. So what's the speed of light through a vacuum compared to what's the speed of light like through that material, right? So N for a vacuum or air is like 1. Well, a true vacuum is exactly 1. Air is pretty close, so I'm going to round it a little bit, right? Through water, I think it was like 1.33. And glass, now there's different kind of glass, right? But kind of a middle number you see quite a bit is like 1.5, pretty close to. Okay, right. So I can tell you, all right, so it tells you how much it's slowing down, right, through each of those media, right? Therefore, refraction, therefore, you can do things like create a magnifying glass, for example, right? I think it's a question coming up pretty soon. Electron vibrates up and down 1,000 times each second, generating an electromagnetic wave, right? Having a, guess what is that? 1,000 times per second. Is that a speed of 1,000 meters per second, a frequency of 1,000 hertz, a wavelength of 1,000 meters, a period of 1,000 seconds? What are we talking about? Is that a frequency? I think that's a frequency of 1,000 hertz, right? That's what 1,000 times per second is. That's a frequency of 1,000 hertz, right? The time period would be 1 over 1,000 seconds, okay? And then the speed of the wavelength is just in, well, that's a different idea. Those could be anything. Or wait, no, that's not exactly true. If it's an electromagnetic wave, the speed would more likely than not be a speed of light, right? 2 polarizing filters held at right angles to each other. The amount of light transmitted equals. I got some polarizing filters right here. Okay? I suppose this is polarizing vertical and vertical, right? You guys got that? If it passes over each other. Okay, so a lot of light gets through. You guys can do this with a lot of sunglasses too if they're labeled as polarizing. Right? But guys, what if I take one of these and turn it 90 degrees? Hey, look at that. Now it's like vertical versus horizontal. Look at that. No light gets through. Right? Is that the answer to that one? 0? Filter? Right? Oh, you know what I don't think I ever did with you guys? All right, you guys want to see something completely insane? Right here. I'm going to bring in a third polarizing filter. Guys, Ray, watch this. This is mind blowing. I forget why this works. This is there's some kind of quantum physics explanation for what I'm about to do. Okay? Now, if I take this third polarized filter, notice there's zero light getting through, right? Everybody sees that, zero light. Okay. If I take this third one and put it on top, okay, there's still zero light gets through. If I put it on the bottom, there's still zero light that gets through. Okay, I mean, that makes sense. Okay. But here's the crazy part. What if I slip this in between these two? Are you guys ready? You guys ready? There's what is it? There should be. Okay. Got this work the other day. Ah, look, there's actually a little bit of light that gets through. Right? This part's actually darker than this part, but I put like more polarizing. Ooh, that's crazy. That's crazy. Ooh. And if you're really curious about that, go search that one. There's something to do with quantum mechanics, I forget. All right. Ooh, these next three questions, let's do these together. I'm gonna skip down a little bit. The color dots that make up a color on, say, it says TV screen, but that could be computer screen, that could be your laptop screen, your phone screen. Right? Because if you zoom down microscopic, there's only three colors. What are those three colors on your screen? Red, green, and blue. Yeah, red, green, blue. It's called the RGB standard, red, green, blue. Okay? Hey, guys, there's only three color detection cones in your eyes, unless you're colorblind. What are those three colors? Red, green, and blue. Right? You got one for each. And from that, your mind can put together all the colors. Right? Red, green, blue. Sorry. Right. All right. So let's skip up. All right. So color seen on a TV, what we were just talking about. Right? What is that called? Is that color addition? Is that what that is? Yeah. Because the more those lights turn on, again, there's only three lights. More of them you turn on, the more it gets to white light. Right? Is if you have all three going on at the same time, the red, green, and blue, is that creating a white screen? Right? White pixel. Right? Here, I got an extra trivia question for you guys. How does your phone screen make yellow? Does anybody remember? Which two light up to make yellow? I think it's like red and green, right? Red and green. Right. It's weird. Right? Now, that's not how paints work, though, right? If you're painting a picture, then it's totally different, right? Guys, what are the three colors in your color printer? And it's not red, green, blue. It's there you go, CMY. Yeah. Exactly. Yeah. Cyan, magenta, yellow. Right. And that's like this question right here. Colors seen on a photograph, paints, color printer, right? Is that color subtraction? Right. Because okay, now of course you have a black ink cartridge also, right? But the three colors, yeah, exactly what Tucker said. You got cyan, magenta, yellow. Right? What if your color printer prints all three of those, cyan and magenta and yellow? What color does it make on the paper? Black. It does. I see. All right. Because every time it's putting on a new color, it's subtracting the wavelengths that are allowed to be reflected from that page. The law of reflection. Ooh, I'll draw you guys. Law of reflection. So this is if you have a mirror. Let's go. Caption behind the mirror. Also, mirror. Mirror. Here's a normal line, right? So I just dashed off a normal line, a line that's normal, say perpendicular to the surface. Okay. Let's say I shine an incident ray right here. Is that gonna bounce off about maybe about that direction right there, right? So that this angle of incidence matches this angle of reflection, right? Would those always be the same, right? That's the law of reflection. Okay. Now we took it an extra step in this class and said, oh, what if you have like a funhouse curvy type mirror, right? This law still applied, right? It just had an interesting outcome. It'd be bigger, smaller, virtual or real of that, right? So law of reflection says, where is it? Angle of reflection equals the angle of incidence, right? Okay. The reflected angle is the incident angle, and with respect to the normal line. Okay. It's always going to be true. A person standing waist deep in a swimming pool appears to have short legs. Ooh. Or throw a straw on a glass of water. It looks all bent. Same idea. Because of what? Guys, what effect is causing that? Refraction. The shortest plane mirror you can see your entire image is. But some of you guys remember this. Right, guys, suppose you're 6 feet tall. How much mirror do you actually need to see your entire self? Yeah, draw this out. Right. So here's let's say that's a dresser mirror, right? Like a plain flat mirror. Okay. So I got a plain mirror right there. Right. let's put a stick figure. Oh, I can put him any distance away. I'm gonna put him over here. Okay. Now, let's see, how far away is he? It's about that many centimeter, bam, bam. But his reflection is probably gonna end up, oh, do my best job. Well, it's probably pretty close to that. Is that about his reflection, you guys think? Right? Right. So let's see, from the point of view of his eyes, where he's looking at himself in this mirror, right? Now, I drew the dresser mirror the same height. You don't actually need the full height. You need less than that. So he looks up, he sees the top of his head. Hey, there's the top of my head. And that light ray came from Baboing from that way. Then he looks down and he sees his feet. Hey, there's my feet. And that light ray came from Baboing that direction there, right? Following the law of reflection. Okay. So to see his entire image, I guess he only needs that bit of mirror right there, right? Right. And what does that compare to his full height? Well, I can measure it, and I'll get you guys the answer that way. So let's see, his full height is looks almost 7 centimeters. He's almost 7 centimeters tall, right? And this is almost 3.5. Almost 3.5 compared to almost 7, right? Is that like half his height? Right. Now the catch is okay. So if you were 6 feet tall, you would only need 3 feet of mirror to see your entire self. The catch is you need it positioned in exactly the right place to do that. Right. So half your height is the answer to that question. A rainbow nicely illustrates an example of light. What? Rainbow. Here. I did create a new poster for this one. I think I printed this one out too. Suppose you got all these misty water droplets floating around in the air, right? Say like after a rainstorm. Right? And here's you off in the distance, got a cartoon version of this course, and you're looking at all that misty air off in the distance. And the sun is directly behind you. Here's the sun. Right? Right? So there's the setup. Right? So now we're setting up the conditions for a rainbow. Now, if you follow one particular ray of light, say here's a ray of light, here's the process. It's going to be a 3-part process. It's going to refract inside this water droplet. It's going to reflect off the back and then refract one more time before it goes to your eyeballs. Boom. Okay? Now, you guys remember things like chromatic aberration? Each wavelength of light, each color will refract at a slightly different angle. Right? That's why you can take a prism and spread the colors out. The Pink Floyd Dark Side of the Moon album cover. Okay. So then that's where you're looking at a rainbow, right? Rainbow. Okay. So you need reflection and refraction. You need both. So refraction, internal reflection. I'm going to go with both of those. You need both of those. Chromatic aberration occurs because different color light rays, say, is going to refract at different angles when passing through a lens, right? So I was just talking about, right? Chromatic aberration. Yeah, that's one of the parts that makes a rainbow possible to see. So back in Galileo's days, when Galileo was looking through his pirate-style telescope, say Jupiter, he's watching the moons of Jupiter go around Jupiter, right? He wasn't really seeing exactly a crisp image. He was seeing it was kind of spread out, like the colors were spread out a little bit, right? Chromatic aberration. Does anybody remember who's the scientist who invented a solution to that? So that, like modern day telescopes, you see some pictures around here. I think those are Hubble pictures up there on the wall, right? Those look pretty crisp because those are not refracting telescopes. Right? What kind of telescope? If you're not using a lens, you could instead use a what? A mirror, right? A mirror, right? Who invented the reflecting telescope? Was it Isaac Newton? It was Newton. He did that one too. Reflecting telescope, Isaac Newton. A magnifying glass underwater will magnify. How compares to the air? Well, let me go back a few pages in my notes. So it's related to, you guys remember this from a few minutes ago? Right? Index of refraction, different material. So if you have a magnifying glass in, I got one right here. I got one right here. It's like I'm magnifying this. Look at that. Right? You guys see it getting bigger? You guys see it get bigger, right? Right. So there's refraction, and then this lens is shaped the way it is, it causes this magnification. And there's two materials I got this glass, let's call it N 1.5, it's probably pretty close. In the air, it's pretty close to 1.0. So there's a difference here. If you go over to Snell's law, it'll tell you, you guys remember Snell's law? It tells you how much some light ray will refract given these indices of refraction. Okay? Now, if you take this glass underwater, notice that the difference is not as much. So is this magnifying glass going to magnify as much underneath the water? No, right? Actually, if these two numbers were the same, suppose my glass was 1.33 and the water was 1.33, right? What would this look like underwater if they were the exact same? It would look, yeah, completely transparent. Wouldn't even know that there was glass there, right? It would be like somebody just took the lens out, right? Right, yeah, it wouldn't magnify at all if they were the same. And so the closer together the indices of refraction, the less refraction and the less magnification. So not as much under the water. The fundamental force underlying all chemical reaction. Hey, a few days ago, we're talking about, remember 4 fundamental forces? What was there? There was gravitational, there was electromagnetic, and then there were 2 nuclear forces, right? Centripetal is not a fundamental force, right? And guys, which one was chemical reactions? That was electromagnetic, wasn't it? So I would circle electrical on this one, right? Right. So when you guys took the class chemistry, there's something to do with valence electrons, right? Why does sodium react with chlorine and give you sodium chloride salt? Oh, okay, something to do with valence electrons at this. So electromagnetic reaction. To be safe in the unlikely case of a lightning strike, it's best to be inside a building framed with what? Ooh, do you want steel or wood? Because if you're suppose you're in a steel frame and your friend's in a wood frame. No, I'll draw that out. Right. Okay. So here's a steel frame. Oh, steel. Right. And here's you. Right. And then you look over and you see your friend in a wood framed building. Wood. Right. And here's your friend. Right. And your friend have a bet going on who's gonna have a more joyous experience. And we're gonna hit both of these with a bunch of lightning. Okay. Guys, does the lightning on the steel frame want to follow the steel all the way down to the ground? Steel all the way ground? Yeah, that's what it wants to do, right? Right? Because steel is really conductive. So that's a path of least resistance, isn't it? Right? Are you pretty safe inside there? Yeah. Right. Hey, are we all sitting in a steel frame building right now? I bet we are, because modern building codes, right? Is that called a Faraday cage? What that's called, Faraday cage, right? Now let's check out your friend over here. Is wood very conductive? Right, not as well, right? You think when we zap this, you think that electricity says, "Where's the point of least resistance? Ah, there's a nice spiky human." Does that? So which one do you want to be in? Let's go with steel. Yeah. 2 charges separated by a distance of 1 meter exert a 20 Newton force on each other if the charges are pulled to 2 meters separation distance. So we're going to double the separation distance. What's the new force in Newton? So this is Coulomb's law. Coulomb's law. So the force, the electrostatic force between 2 charges goes electrostatic constant times the first charge times the second charge. This gauge should be in some number of coulombs divided by the distance squared, right? Which looks a lot like universal gravitation, doesn't it? Say the force between the Earth and the Moon, that could be GMM over R squared, right? It's the same structure, right? So we're looking at proportional changes. As if you double the distance between these 2 charged particles, what's a factor of 2 squared? Is that 4? Right? And since this is a denominator, it's 1 over that, right? So guys, double the distance is what fraction of the force? 1 over 4, right? Got that, right? Now, if the original force then was 20 newtons, what's 1/4 of that? 5 newtons. Okay, is that right? So say we're going to double the distance from 1 to 2 meters. That's double the distance. That factor squared, and then 1 over that, that's 1/4 of the force. 1/4 of 20 newtons is 5 newtons. Boom, boom, boom. You guys navigate that? Electrical resistance in a wire depends on the wire's. See what? Hey, do you guys remember recently doing a Play-Doh resistivity lab? So you had a cylinder of Play-Doh, it would conduct electricity. Right? You could separate it, throw an LED on there, and light up the LED. Right? So let's see, this has some cross-sectional area, I'll call A. This has some length, I'll call L. Label that right here, L. Right? And has some, well, it's some material. Maybe it's Play-Doh, maybe this is a wire made out of aluminum. Maybe it's a wire made out of copper. Right? So I'm gonna put some letter rho to represent the resistivity. Right? And then the resistance from end to end, from bam, bam, that resistance is, you guys remember it's resistivity times the length divided by the cross-sectional area. Okay, the longer the length, the more the resistance end to end. The wider the wire, the less the resistance. Inverse relationship. And there's also some material property. Okay, so check that. Compared to thin wires, thick wires, I think thick wires is not as much resistance. Is that going to be less resistance then? Yeah. Yeah, it's that brown box over there.
Oh, yeah, I think so.
All right, so you guys got that? All right. If you increase this cross-sectional area, that would be decreasing the resistance. You guys see it? Inverse relationship. Right? Okay. And like before, you can plug in some numbers if you like, right? But if you divide by larger numbers, you get smaller overall fractions.
Thanks so much.
Yeah. The primary reason a bird can perch harmlessly on bare high voltage wires. Let's look at that scenario. Okay. So say you're looking at, here's a wire up here between power lines, and it's up at like 10,000 volts, maybe, right? Could be, right? Or maybe even more than that. Right? Here comes a bird. He puts down one foot, he's okay. Right? He puts down the other foot, is he still okay? Yeah, he's still fine. He can fly off, and he's all fine and good. Right? Because what if you take 2 leads of a Christmas light? Right? You guys remember working with those a few weeks back, and you attach them both to the positive terminal of the battery. Positive, positive. Does the light light up? No, because there's no potential difference. You connect the positive to the negative. So under one foot it's 10,000 volts. On the other foot it's 10,000 volts. Guys, what's the difference between 10,000 and 10,000? Zero difference. So there's no potential difference. So there's no impedance for the electricity to flow. All right, so I'm going to go with, see, where is it? There's no potential difference beneath the bird's feet. Right? Sometimes we just call it voltage, but there's no difference. When 8-volt battery connected to a resistor, 2 amps of current flow, what is the resistor's value? I'll show you guys a couple of formulas here. You guys remember Ohm's law? This is probably good to put on your study guide. You could do this. You could do V equals IR, or more often than not, I like the fraction form of it. The current that flows is equal to the potential difference voltage over the resistance. Right? There's also here Joule's law. Joule's law. Right. I gave you guys 3 different versions of Joule's law. There's power equals current times voltage. You could do power equals current squared times resistance, or power equals voltage squared divided by resistance. All right, so there we go. Right, you guys remember those? Boom. Ohm's law, Joule's law. Right, so what's this question? 8 volts, 2 amps. What's the resistance? All right. So here I got 8 volts. Here's 2 amps. What's the resistance? You see it? All right, 8 volts here, 2 amps here. Guys, what's 8 divided by 2? 4, right? Or if you like, 2 times 4 is 8. So I'm looking at 4 ohms, right? And of course, when you guys get this exam and all the numbers are changed, you can still apply Ohm's law, right? You guys do that? Because you just wrote down Ohm's law in your study guide, and so you'll have that. When connected to 110 volts power supply, how much current through a light bulb with a resistance of 220 ohms? Let's see, they gave us how many volts and how many ohms of resistance. What's the current? That sounds like this form of Ohm's law right here. Right? So what was the numbers? It was 110 volts, 220 ohms. Guys, what's 110 volts divided by 220 ohms? 110 over 220. Is that 0.5? Yeah, there you go. 0.5 amps. 0.5 amps. That's it. 0.5 amps. Okay. So you guys can apply Ohm's law, right? Ohm's law. A light bulb plugged into 120 volts outlet. Hey, is that what we got in this room? These outlets in this room, those are 120 volts. In America. We got a 0.7 amp current. What's the power? Oh, power rating. Ooh, we're flipping over to Joule's law. Got volts, we got amps. That sounds like this one right here. So try this in your calculator. We got 0.7 amps times 120 volts. What is 0.7 amps times 120 volts? You guys getting 84 watts? So what's on your screen? It's fine. Find my own calculator here. So I said 0.7 amps times 120 volts. Yeah, that's 84 watts. 84 watts. Okay. A closed circuit is a circuit in which charge, say, cannot flow or can flow. Guys, if you close the circuit, that's a path for the electricity to flow. So can flow, you're gonna go with, right? So that's like hitting the on switch on a flashlight. If you hit on, you're closing the circuit. Okay? If you hit the off switch, that's gonna open the circuit and then the electricity stops flowing. Okay? So here's closed, open, on, off. Okay? Closed is on, open is off. As more lamps are put into a series circuit, the overall current in the circuit. Okay, this one's kind of a two-parter. So we draw you guys. Let's do series and then parallel because there's got to be some parallel questions coming up too. Okay, so here's 1, 2, 3 resistors in series, possibly light bulbs. It could be. Okay, versus. Let's see, how am I going to do parallel? What if I do we do like this? Okay, got 1, 2, 3 in parallel. Right? Is that right? And then maybe got some voltage source over here, possibly. Maybe like that. Right? You guys remember Paul Hewitt had the 12-volt car battery? Okay, he hooked them up, and first you started series, and then did parallel. Okay. So here's your series. Here's your parallel. Okay. What's the total resistance in series? Gonna just do R1 plus R2 plus R3 plus ... Just keep adding them like that. Okay. Now for parallel, you can either use the fraction method. 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. Okay. Or if you just got two resistors in parallel, or if you just do 2 at a time, then can you do, let's see, for 2 resistors in parallel? Okay. What was the rule? You could just jump straight to the equivalent resistances, what over what? Was it product over sum? Is that what you guys were doing? Okay. Okay. So I might do like resistor A times resistor B over resistor A plus B, resistor B, like that, right? And you can navigate that, just have to do 2 at a time, right? So we got that. There was something else about this question. Oh, it said overall current. So I'm also gonna, in the corner, put Ohm's law. Ohm's law. So current, I remember, was potential difference over resistance, maybe the total resistance, something like that. Okay. So we're starting in series here. Yeah. Right. So part 1, as you put more and more and more bulbs in series, what's happening to the total resistance? Is that also increasing? Is that okay? Now let's bring that over to Ohm's law. Okay. So we got some potential difference. There's some battery maybe hooked up here. Here, I'll throw a battery on here too. Okay. Boom, boom. Oh, there's a battery. Okay. 12 volts or something. Okay. Okay. And we're dividing by a larger and larger and larger resistance. What's happening to the current? It's getting less and less. You guys see that? Okay. And again, inverse relationship. 12 volts over 3 ohms. That's 4 amps. 12 volts divided by 6 ohms. That's only 2 amps. As you pump up the resistance for a given voltage, you're getting less and less current. As more lamps are put into a parallel circuit, the overall current in the circuit. Okay, so now we're switching over this one. right, so here, I'll walk you guys through two different ways to think about this. One way is kind of the way we just did it for series. When you add more and more in parallel, what happens to the overall current? Or sorry, so overall resistance, I meant to say. Guys, overall resistance is getting less and less and less, right? Guys, remember, this is the same math as people teaming up to paint a fence. The more people you have painting the fence, the less time it takes. The more resistors you have in parallel, the less is the overall resistance. Okay, so now run over to Ohm's law. Okay, so we got some given voltage, maybe like 12 volts battery. Okay. Now we're divided by smaller and smaller resistances. Now what's happening to current? It's getting more and more. It's increasing. Okay. So that's one way to think of it. Here's another way to think of it. You guys remember when you did this lab, or when Paul Hewitt was doing it, and you were putting on more and more bulbs like rungs of a ladder? What happened to the brightness of the bulbs that were already there? They just shone as bright as they did before, right? Got same potential difference across them, same resistance, right? So from the battery's point of view, every time you add on another bulb in parallel, it's like, oh, well, okay, I have to supply that one also. Okay, when you got another one, okay, I got to supply that one also. So that's more and more and more current being drained from the battery. Okay. All right, so however you think of it, you get to the same answer. All right, so the overall current is increasing as you put more in parallel. When one light bulb in a series circuit containing several bulbs burns out. Ooh, let's look at that. So series circuit, let's say this one burns out. Does that open the circuit? Right? And then none of the other bulbs even turn on. That's the answer to that question. None of the other bulbs light at all. Right? When one bulb in a parallel circuit containing several bulbs burns out, the other bulbs. So let's take this one in. That one burns out. Hey, is there still a path for the electricity through these other two? There is. In fact, they're going to burn just as bright as before anyway. That's true, right? I've seen both kind of Christmas lights. If you buy a string of Christmas lights and one bulb burns out and therefore the entire line burns out, then you know they were connected in series. If one bulb burns out and the other stay the same as they were before anyway, and they're still lighting, then you know they're wired in parallel, right? More often I see that design, but a short circuit. A short circuit. Hey, is that when you say take a paper clip and hook the positive directly to the negative terminal of a battery? Right? And there's basically zero resistance, and it burns the battery, drains the battery really fast. Positive connected directly to the negative wire. Yep. All right. Okay, I'm reading the other answer choices. I think that one's the best answer though. Right? Connect the positive directly to the negative with no resistance. Right? Ooh, if you drop your cell phone in a glass of water, first, avoid doing that because that'll short it out, won't it? Short it out, right? Because now there's paths for the electricity to flow that's not through the original circuitry. The total resistance of 10 ohms and 7 ohms in series. Ooh, well, you guys just wrote down this formula in your study guide. So guys, what's 10 and 7 in series? What is that? 17? You guys got 17? Okay. Right. Number 88, 6 ohms and 12 ohms in parallel. Right? Okay. Well, you could do product over sum. That's one way to do it. Right. Let's try 6 and 12 in parallel. Go kinky this one. Okay. So resistance equivalent is, so it's 6 times 12 over 6 plus 12. That'd be some number of ohms. That's product over sum. Okay. 6 times 12 is 72. 6 plus 12 is 18. That's like 4 ohms. Right? Product over sum of 6 and 12 would be 4. Okay. Hey, what about this? What if you're teaming up to paint a fence? You could have done the whole job yourself in 6 hours. You're getting with a friend who could have done the whole job himself in 12 hours. Now you're working together in parallel. Could you knock out that job in 4 hours? That sounds about right, right? It's the same math. Okay. Guys, one thing I want you guys to get out of this class too is like all the stuff you guys are learning in here, there's really close cross applications to a lot of other things too. I know all these formulas we've been doing with like Ohm's law and Joule's law and resistors and series and parallel. Okay, yeah, that's all for electricity. But you could also apply this to similar situations. Right? If you're designing a pipe system to go around, feed water to an entire city, right? That's analogous to all this. if you're watching traffic flow, right, we're going to build a new road. How's that going to change the flow of traffic for like the entire city? Got a network of roads. You can treat this as series in parallel. If you're designing some big construction project, it's like, okay, well, some parts we have to do sequentially. So we can't build the 5th floor until we build the 4th floor first, right? That's like a series situation. Some parts we'll do in parallel. Hey, we can have the guy wiring up all the wires in the building at the same time the plumber's putting in all the pipes and the plumbing, right? That could be parallel, right? So then how long is it going to take to do the whole job? Well, some parts are in series, some parts are in parallel, right? If you break a bar magnet in half, each half, oh, I can do that right here. Here's a giant magnet, right? This is effectively one magnet. It's got like a north pole and a south pole, right? What if I break that in half? Hey, now are these two tiny magnets and they each have their own north and south, right? What if I broke it in half again? Would each one still have a north and a south? Yeah. Can you have a unipolar magnet with just a north and nothing else? No. Has to always be dipole. Has to have a north and a south. Right. So I'm going to say becomes two tiny magnets with each with two poles. Each half becomes a bar magnet with two poles. Okay. You guys got magnets. How do they work? A device consisting of a coil that is mechanically rotated in a stationary magnetic field. Okay. Now, I have posters for almost all these anyway, but this one, oh, here. I got some posters. Oh, at least this one, this poster right here. All right, so I got two really similar devices that are doing exactly opposite processes. See, generator and motor, but okay, so which one's which? Right? So a generator is taking mechanical motion. So it could be a waterfall turning a paddle wheel. Most electricity generated is you boil water to have steam turn a turbine. And you're going to force a wire past a magnet. And you have to force it past because you guys remember Lenz's law, right? There's a resistive force, right? Right. So we're forcing a wire past a magnet that is generating electricity. Oh, so now we've got the energy on electric current. Right? Some about right-hand rule tell you right, which way the current's going to flow from that. Right. Right. Okay. So great. Now we got electricity on the electric grid. Now we're going to bring this over to. Okay. Let's say this building. Ooh, I hear the air conditioning going. You guys think there's some motor in there that's like turning something, right? Mechanical, right? We're going to take this energy in the form of electric current, run that through a wire past another magnetic field. That's going to create a force. You guys remember creating a motor in class? I gave you guys some paper clips, some wires, some batteries, and a stack of magnets. That's all you needed, right? Right. And you guys created this, and it started spinning. You guys remember that? Right. So now we're going from electrical back to mechanical. Right. So which one is this one? Right. Device consisting of a coil mechanically rotated in stationary magnetic field. That sounds like a generator. Sounds like that one, right? For mechanically rotating this coil in this magnetic field, that's a generator. The next question, a device that transforms electrical energy back to mechanical energy. Hey, that's this one here. That's a motor. So we've got a generator and a motor. Right. You guys got that? Generator, motor. Most commercial generators are driven by, right? How is the vast majority of electricity generated on the grid? Are you boiling water, turning that into steam, and the steam is running a turbine? Right? That's how you get energy from coal. That's how you get energy from natural gas. That's how you get energy from nuclear. Right? It all goes through the steam, the Rankine cycle. Quantum time. You guys ready for quantum? Light behaves as well, I know light's a wave, right? There's the double slit experiment, create an interference pattern. But I also remember this photoelectric effect. Light also had these particle properties too. Right? Both of those are true. So yeah, light has this dual nature. It's both a wave and a particle. A photocell can be activated with the blue light, but not with the red light. I got some more posters on this one too. Let me find my photoelectric effect poster somewhere here. There's the photo electric effect. All right. Okay, you guys remember this? So photoelectric, this is Einstein interpreted this as light has particle-like properties, right? Because if you double the frequency past the threshold, then you'll double the energy you can get from it, right? But maybe this can get energy, not in the red part of the spectrum, but in the blue part of the spectrum it can. Because we just increased the frequency. From this red to this blue. Right, could be do that. All right, so over here. Photocell can be activated with a blue light, but not a red light. That sounds like the photoelectric effect because the blue light has a higher frequency, right? I was just showing you guys a higher frequency. Higher frequency. Right? You guys got higher frequency. Photoelectric effect. The wavelength of a particle. Ooh, does that sound like de Broglie wavelength? You guys remember this de Broglie wave-particle duality? Now, if you apply this to electrons, that could set up these electron configurations and explain pretty much all of chemistry. Remember that too? De Broglie wavelength. The discrete orbits of electrons are best understood by considering the electrons. Right? Remember, why is it that these electrons only fill certain orbital spaces? Because of their particle property or the wave property? The wave property. Right. You have to close the full number of wavelengths. Looking at wave properties. Wave properties. Okay. You guys got wave properties? Explain the discrete orbits of electrons. Number 97. Nuclear fission. Ooh, nuclear fission. I got, I think, yeah, these last 4 questions are about this poster right here. Right? Fusion versus fission. Okay. So if you say something like, what's the mass of a nucleon, say a proton or a neutron, that actually depends which atom it's in, right? Or in this case, what's the binding energy per nucleon, right? So here's hydrogen, here's uranium, right? Uranium is the largest naturally occurring element in our particular solar system, right? And remember, anything beyond helium basically was probably created in a nova event about 4.5 billion years ago, just in our solar system, and it goes up to uranium. Other solar systems might go bigger than that, but we only get up to uranium naturally anyway. Okay. Now, if you split a uranium into smaller atoms, say krypton and barium, then you'll get extra energy out because there's a height change on this graph, right? That's fission. So we're taking heavy elements like uranium and splitting them in half. Right? There's fission. Okay. The other way you can get nuclear energy is fusion. That's if you fuse together. Usually you're going from hydrogen to helium. That's the main way. You guys see it's a much bigger jump on the graph. It's like hundreds of times bigger, almost 1,000 times bigger. Right. Okay, so we're fusing together these different isotopes of hydrogen to make helium and get like almost 1,000 times the energy from that reaction. Okay. The trouble with the fusion is we haven't quite figured out how to make a power plant with this yet. Right. So all our nuclear power plants right now are all fission. Right. And then all the problems you hear about nuclear, well, are really fission problems. Right. Oh, no, we can make bombs out of both of these, right? Like a thermonuclear bomb, that's a hydrogen bomb, that's a fusion type bomb, right? But can you make a power plant with that? Hopefully sooner rather than later, but that is a uncracked engineering problem as of today. All right, so back to these last 4 questions right here. Nuclear fission occurs when, say, a nucleus divide. Right, let's go with here. Let's go with this one. Electrical forces in a nucleus overpower the nuclear forces, right? It's like if you're bombarding a U-235 atom with neutrons, then at some point you're going to split the nucleus, but you're using electrical forces to do that. Okay, you guys got that? Right. Electrical forces overpower nuclear forces, split the atom. Right. That's fission. Nuclear fusion releases energy when. Great. Now here I'm already thinking we're probably fusing together 2 hydrogens to make a helium. How about this one? Very light nuclei fuse together. It's not uranium, it's not heavy ion. No. So very light nuclei like hydrogen fuse together to make helium. The primary fuel for nuclear fusion is, I'm looking for hydrogen. Here's hydrogen right there. Actually, it's different isotopes of hydrogen. There's deuterium and tritium. You got extra neutrons. Makes this process work a little easier. A nuclear process that has relatively few radioactive byproducts. Well, I know one of the problems with nuclear power plants today, which of course are fission plants, is that we got this nuclear waste that's going to be radioactive for tens of thousands of years. How do we safely store it so it doesn't contaminate the environment? How do we tell people 10,000 years from now, stay away from this? Those are all problems with fission, right? But fusion, fusion is the one that's way cleaner. So you don't have nearly as many radioactive byproducts. Yeah. So fusion, not only is it almost 1,000 times the energy, and not only is the energy source like way more abundant, but it's also cleaner too. Right? So it's got all those advantages going for it. All right, there you go. There's the exam review.